Hi, we're the Self-Charging Battery Group. Our team members are Aaron Atnip, Adam Dallin, Tanner Nelson, Connor Siri, Jeremiah Young, and myself, Jonathan Johnson. The design problem that we took over the last 2 semesters was proposed by the University of Utah's Advanced Energy Innovations Lab, headed by Dr. Roseanne Warren. Dr. Warren and her team have been researching the use of polyvinylidene fluoride, or PVDF, as a separator in a lithium-ion battery. PVDF is a piezoelectric material, which is interesting because it creates a voltage difference over its cross-section when it is subjected to stress or a large change in temperature over time. We can quickly see why this is interesting for the use in a battery, because if we quickly heat, cool, or even subject the PVDF inside a battery to stress, it will theoretically allow a battery to charge itself internally. This is really nice because small batteries used in dynamic environments could charge themselves when being used. For example, if you had a flashlight and you're on a camping trip or something, when you use a flashlight, the light bulb is going to heat the battery up if it's in close proximity, so it will charge itself internally. Also, if you have a small TPMS sensor inside your tire while you're driving, stopping and going, it's going to have a large temperature difference over time. So the design objective that we were given was to design a spectroelectrochemical cell, or a battery, that can be used in a UV visible spectrometer to observe the state of charge in the cell. A UV vis spectrometer sends light through a cell and measures the transmittance or reflectance over certain wavelengths. This is accomplished by measuring the change in color of the electrodes in the battery as ions flow from one to the other. UV vis spectrometers have a small 10 by 10 millimeter footprint, so the cell that we designed has to be very small. We were also tasked with designing a method to quickly heat the PVDF inside the cell. Obviously, this is the big thing. This is really the bulk of our work, was make sure that it can heat up so that we can see whether it actually will charge this battery internally or not, or to what extent that it will. Other major requirements include a fully sealed cell, ease of assembly, and a limit on the maximum temperature. This is because the electrolyte won't function properly when it comes into contact with oxygen, and it could become a toxic gas if heated over 70 degrees Celsius. Also, the cell is going to be assembled inside a glove box to keep oxygen out. This is where the sealing comes into place. It needs to be sealed inside the glove box, and once taken out, it shouldn't leak because the oxygen will pretty much render the electrolyte useless. So this glove box is difficult to use, it's bulky, so this in itself is a challenge. So because our design is research-based, our end users or our customers will be Dr. Warren and her research team. This design was proposed because the Advanced Energy Innovations Lab did not have a reliable way to heat the PVDF and test the effects of heating. Aaron will now discuss how we created a design to meet our objectives.
The unique design requirements of our project led us to develop two alternate cell designs, one using a standard scientific cuvette and the other based on a conflat disk. As Johnny mentioned, our test cells must be resistant to high temperatures, completely airtight, and compact enough to fit in a UV-Vis spectrometer. For the cuvette cell design, airtight sealing was accomplished using a silicone gasket, compressed between an aluminum lid and the top of the cuvette. This customized lid design allows for 256 threaded screws and nuts to tighten the components and ensure compression of the gasket. Through-hole components are sealed with the application of rubber polymer RTV. This cell is heated using a 50-watt cartridge heater. CFD heat flow analysis was performed to estimate the heater size and the watt density needed to deliver the heat rate desired. A stainless steel heater cover and conducting sleeve are used to distribute the heat more uniformly across the cell and increase the heat rate towards the bottom, where the PVDF material is secured. An elliptical viewing window is machined into the bottom of the conducting sleeve to allow UV light to pass through during measurements in order to determine the state of charge. The conflat disk cell is hermetically sealed using a compressed O-ring design. Groove steps machined into the cell body allow battery components along with a rubber O-ring to fit in the cell. The disk cell components are compressed together by the top viewing window and secured by screws. Heating of the disk cell is accomplished using a Peltier device, which is a compact solid-state active heat pump that transfers heat from one side of the device to the other. An advantage of the Peltier device is that it's easy to control and heats up relatively quickly. The heat input to the disk cell is controlled using an Arduino script that helps to regulate and to stabilize the temperature.
There were three main metrics that each of our designs were subject to: a desired heating rate, desired sealing pressure, and desired max temperature. These were 1 degree C per second, 20 psi, and 60 degrees C, respectively. Hard caps of sealing at room pressure and a max temperature of 70 degrees C were enforced due to safety concerns. Additionally, our cells had to function well as batteries so that they would be useful for Professor Warren's lab to use in future testing. Both cells were able to accomplish this. Heat rates were tested with water, the respective heater, and a thermocouple in order to guard against boiling or electrolyte. The heating was managed through a pre-calibrated on-off Arduino program for the disk cell and a timer with predetermined on time for the cuvette cell. The max temperature and spatial limits hindered our cell's abilities to get to the desired heat rates. The issue of maximum temperature was somewhat alleviated by pre-cooling our water. Without these limits, and still in the confines of the small cuvette cell, we were able to reach a heat rate of 3.86 degrees C per second. With these constraints added, heat rate results were 0.8 degrees C per second for the cuvette cell and 0.67 degrees C per second for the disk cell. Maximum temperature values were on target at 58 degrees for the disk cell and 52 degrees for the cuvette cell. Sealing capability was tested by filling a cell with helium gas until leakage occurred. Both of the cells performed well, with the disk cell obtaining a pressure of 30 psi and the cuvette cell obtaining a pressure of 40 psi.
We will now demonstrate our cells in action, beginning with heating. First, we hydrate the cell with pre-cooled water to optimize our heat transfer. Then insert the 50-watt heater and turn on the timer to begin powering the heater for the specified time. This is a sped-up plot of the water temperature within the heater running for the specified amount of time and the temperature stabilization after shutoff. We then move to our Peltier controller, which shows the temperature readout from the Arduino and the Peltier being switched on and off to stay within our upper and lower temperature limits. Our next demonstration is merely a visualization of UV-Vis testing. Our cells are complete and ready for testing, which we will perform prior to the end of the semester. We set the disk cell on the reflectance portion of the spectrometer, which then emits light that reflects off the cell into the collector, letting us know if the cell is receiving any charge from the PVDF through slight color changes of the collectors. Similarly, the cuvette is inserted into the slot shown. However, this particular setup will allow light to fully pass through the cell, as shown by the arrows, rather than using reflectance. This will still allow us to measure slight color changes of the collectors to identify a charge.